Module 4 Mastery Assignment by Leslie Orr. Topic 1. Approximating the integral numerically. We can approximate the integral numerically through a use of table of values to construct a Riemann sum. Riemann sums are methods used to approximate an integral using sums of areas. There are 4 different types of sums we can look at. There's the left-hand sum, which relies on the use of the left-hand height of each section of the function. There's also the right-hand sum, which relies on the use of the right-hand height of each section of the function. And there's a trapezoidal sum, which relies on the use of areas of trapezoids to approximate the integral. And then there's the midpoint sum, which relies on the use of the midpoint height of each section of the function. We can also compare the values of the 4 sums. Since all of them are only approximations, they will either be underestimates or overestimates, and we take into account 2 main factors which determine this. First, is the function increasing or decreasing? And second, is the function concave up or concave down? Here are 2 charts to help remember this. If a function is increasing, then the left-hand sum will be an underestimate and an overestimate if the function is decreasing. This is the opposite for the right-hand sum. When looking at concavity, if the function is concave up, then the trapezoidal sum will be an overestimate, but if the function is concave down, then the trapezoidal sum will be an underestimate. The midpoint sum will have the opposite characteristics when looking at concavity. Now that we know these things, let's look at an example. A rocket has a positive velocity after being launched upward from 0 feet as the initial height at t equals 0 seconds. The velocity of the rocket is recorded from selected values of t over 0 to 80 seconds as shown in the table. Use a midpoint Riemann sum with 3 equal subintervals to approximate the integral from 10 to 70 v of t dt. First, we're going to look at the length of the interval from 10 to 70, which is 60, then divide by 3 to get the length of the subintervals. The length of each subinterval will be 20 seconds, so here I've drawn the length of each subinterval, which is going to be from 10 to 30 seconds, 30 to 50 seconds, and 50 to 70 seconds. The middle height would be found 10 seconds between each of those values, so it's going to be 22, 35, and 44 feet per second. Now that we have our values, we can find our midpoint Riemann sum. Rectangle 1 will be 20 times 22, which is going to give us 440 feet. Notice how the units of the seconds cancel out, which is how I got feet. Rectangle 2 will be 20 times 35, which equals 700 feet. And rectangle 3 is 20 times 44, which gives us 880 feet. Now we can combine the areas of all our rectangles to get 2020 feet over the interval 10 to 70 seconds. We can also predict whether a sum will be an underestimate or overestimate by looking back at the table. From the table, notice that the function is increasing, so the left-hand sum will be an underestimate while the right-hand sum will be an overestimate since the value on the left will be lower than the right. In addition, the differences in velocity are decreasing or getting smaller, which indicates the function will be concave down. So trapezoidal sum will be an underestimate while midpoint sum is an overestimate. We can also calculate the other Riemann sums using the table of values given. For our left-hand sum, we're going to use the left-hand heights that are given. So we're going to get 20 times 14 plus 20 times 29 plus 20 times 40, which is going to give us 160 feet over this interval, 10 to 70 seconds. The right-hand sum is found using the right-hand heights given. So we're going to do 20 times 29 plus 20 times 40 plus 20 times 47, which is going to give us 2,320 feet over the 10 to 70 second interval. The trapezoidal sum will take into account both of the values since in a trapezoidal sum, the area formula is 1/2 times height times base 1 plus base 2. So we're going to get 1/2 times 20 times 14 plus 29 plus 1/2 times 20 times 29 plus 40 plus 1/2 times 20 times 40 plus 47. And that is going to give us a value of 1,990 feet over the 10 to 70 second interval. Topic 2. Finding the definite integral using known geometric shapes. First off, we need to know some key terms. A geometric shape is a region that has a known formula for area. The definite integral is the net signed area bound by a function and the x-axis, and the limits of integration are endpoints of domain on which integral is being calculated. Here are some important area formulas to remember. Rectangle is base times height. Square is side squared. Triangle is 1/2 times base times height. Trapezoid is 1/2 times height times base 1 plus base 2. And the area of a circle is pi r squared. However, most of the times it's either a semicircle or a fourth of a circle, so you just divide by 2 or 4. An important thing to understand is what is a net signed area. When you integrate a function, part of it could be above or below the x-axis. So a positive signed area means that the region is above the x-axis, while a negative signed area means that the region is below the x-axis. When you find the net signed area, you're going to net out the positives and negatives over an interval. Now that we know these things, let's look at an example. Here we are going to use the graph of f of x to find different definite integrals. First, let's evaluate the integral from -5 to -3 of f of x dx. Let's first note the limits of integration, which are from -5 to -3. Recall that the area of a circle is pi r squared, and since we are finding a semicircle, we divide it all by 2. So when we plug it in, we get pi times 1 squared divided by 2, and this simplifies to pi over 2. We are going to leave it positive since the area is found above the x-axis. We can also evaluate the integral from -3 to 1 f of x dx. Again, we're going to first look at the limits of integration, which are from -3 to 1. Recall that the area of a circle is pi r squared, and since we are finding a semicircle again, we divide it all by 2. So when we plug it in, we're going to get pi 2 squared over 2, which simplifies to 4 pi over 2, which then simplifies to 2 pi. However, don't forget the signed area. Notice this is below the x-axis, so we're going to get -2 pi as our final answer.